Today is November 24th, and I would like to explain the result of my research on developing of cadmium-mangan telluride integrated optical isolator, the isolator for monolithic integration. The optical isolator is a device which is transparent in one direction and blocks light in opposite direction. An optical isolator protects optical devices from unwanted back reflection. The back reflection is unavoidable for any optical system and can severely disturb its normal operation. In particular, an optical laser, an optical amplifier, and obsessive isolator substantially suffers from back reflection. There are many optical isolators which are used in present high-speed optical networks. The bulk-type optical isolator is commercially available and has a perfect performance, such as a very small insertion loss and a high isolation. The bulk isolator is made of magnetic garnet, which is best transparent magneto-optical material. However, it is difficult to integrate the optical isolator into a photonic integrated circuit with other optical components. It is because the fabrication technology of magnetic garnets is rather different from fabrication technology of conventional optical components. The reason why the garnet cannot be avoided is necessity to have a magneto-optical material for the operation of the optical isolator. The operation of optical isolator based on the non-reciprocal effect or the breaking of the time-inverse symmetry. This slide explains why. For example, when light passes through the magneto-optical crystal, its polarization is rotated because of the Faraday effect. When the light is back reflected, its polarization is rotated in the opposite direction because of the Faraday effect is a non-reciprocal effect. The light polarization can be rotated also in a non-magnetic anisotropic material. However, the reflected light always restores its initial polarization because of the reciprocity of any non-magnetic material. Using the non-reciprocal Faraday rotation, the optical isolator can be fabricated just by placing a polarizer and analyzer at both sides of Faraday rotator. The Faraday rotation and angle between axes of polarizer and analyzer should be adjusted to 45 degrees. Then the polarization of light rotates plus 45 degrees in forward direction, and light can pass the analyzers in forward direction. However, in the backward direction, the polarization is rotated minus 45 degrees. As a result, the backward light is fully blocked. These animations show such a non-reciprocal operation. As for integrated isolator, there are two major requirements for it. The first requirement is ability for integration. It means that the isolator fabrication technology should be well compatible with already existed fabrication technology of the photonic integrated circuits. It has no meaning to fabricate a standalone integrated isolator. The second requirement is the isolator's small size, simplicity, high isolation, and low insertion loss. The isolator is not the main functional element of photonic circuit. The integrated isolator should show the best performance, but meanwhile it should not disturb the functionality of the photonic circuit, and it should not make the photonic circuit more complex. Now, there are three technologies which are fit to those conditions. The first technology is the wafer bonding, which have been developed by Professor Mizumoto from Tokyo Institute of Technology. In this technology, the garneted photonic circuits are fabricated separately, and next they are glued together by the wafer bonding. Since recently the wafer bonding become matured and robust technology, the wafer bonding becomes the mainstream for the integrated isolator. The second technology is the monolithic integration, when a magneto-optical film is grown epitaxially on top of photonic wafer before microfabrication. Next, the photonic and MO materials are processed together. The third technology is hybrid integration, when a ferromagnetic metal is deposited on top of already fabricated photonic circuit. A MO effect is very strong in ferromagnetic metal, and it is relatively easy to deposit an amorphous or polycrystalline metal on top of photonic crystal. Plasmonic isolator also belong to this technology. Today I will talk about monolithic integration. The cadmium-argon telluride is a good fit for monolithic integration. It is a diluted magnetic semiconductor which has thin-blende crystal structure, the same as that of gallium arsenide and indium phosphide. Therefore, cadmium-argon telluride can be grown epitaxially on gallium arsenide or indium phosphide. The magneto-optical effect is large in cadmium manganese telluride. As you can see here, it's compatible to that of the garnets. As in any semiconductor, the refractive index of cadmium-argon telluride increases when the light wavelength becomes close to the band gap. Therefore, the optical confinement in cadmium-argon telluride can be achieved by change of manganese concentration. When I had started the fabrication of cadmium-argon telluride waveguides, there were three challenges I faced. The first challenge was a substantial optical loss, which is due to a large lattice mismatch between gallium arsenide and cadmium telluride, and substantial number of dislocation in waveguide core. The loss was so large, so light cannot propagate longer than 1 millimeter. The problem was solved by optimizing the growth technique. The dislocation, so-called the misfit dislocation, were restricted at gallium arsenide cadmium-argon telluride interface, and there was no dislocation which penetrates the waveguide core, so-called the threading dislocations. As a result, the waveguide became fully transparent with negligible loss. The second challenge was substantial TE mode mismatch, which is due to a difference of effective refractive index for TE and TM waveguide modes. The TM mode mismatch suppresses the Faraday rotation. As a result, the isolation function vanishes. The problem was solved by using more complex waveguide structure, and nearly 100% more deconversion efficiency was achieved. The third challenge was a very narrow operational bandwidth of cadmium-argon telluride isolator. The cadmium-argon telluride is semiconductor. Its Faraday rotation is large near the band gap, but it exponentially decreases when light wavelength turns out of the band gap. The operation of isolator required 45 degrees of Faraday rotation. Even so, a high isolation can be achieved at one wavelength. The isolation degrades even at tiny wavelength tuning. The problem was solved by using quantum well structure. This slide shows the experimental measurements. Since this research requires a lot of material optimization, I have used a Prism couple setup, which does not require any microfabrication, so it could be done faster. A gallium phosphide prism was used to couple laser light into a waveguide. A high sensitivity camera detects the scattering light. A polarizer was fixed in front of the camera in order to measure separately TM and TM polarizations. In absence of magnetic field, there is no Faraday rotation, and only one polarization, the same as the input polarization, can be detected. When the polarization is orthogonal, nothing can be detected. This is a streak of propagating waveguide mode. The first result which you can see is that the waveguide has practically no loss. For my first cadmium mangan telluride waveguide, I could not see a streak longer than 1 millimeter because of high loss. For this waveguide, streak intensity does not change over length over 1 centimeter. It means a very low loss. Next, a magnetic field is applied. The streaks of opposite polarization shows up. Both streaks are modulated, and minimum for one streak correspond to maximum for streak of other polarization. It is because of the polarization rotation. One polarization transforms into orthogonal polarization with propagation of waveguide mode and vice versa. The second result which you can see is that nearly 100% more conversion efficiency is achieved. You can see that this practically no light at the minimum. It means the full conversion. As was explained earlier, there was a problem of narrow operation wavelength range. It was solved by using quantum well structure like that. This graph shows the Faraday rotation measured for waveguide without and with quantum wells as function of wavelengths. In case of waveguide with quantum well, the wavelength dependence of Faraday rotation is nearly flat. This is raw data measured at different wavelengths for waveguide with and without quantum well. In the case of waveguide without quantum wells, the oscillation period is very different at different wavelengths. In contrast, in the case of waveguide with quantum well, the period is practically the same. Additional good result is that in case of waveguide with quantum well, the oscillation period is very short, meaning a very high Faraday rotation. This slide shows the isolation measurement using two-prism method. A laser beam is coupled into waveguide by one prism and coupled out by another prism. The output light is detected by a camera. There is a large light output for one propagation direction, and the light is fully blocked when the light propagation direction has been reversed. A rather big isolation was achieved. So in conclusion, cadmium mangan telluride is excellent material for integrated optical isolator. In cadmium mangan telluride waveguide, 100% mode conversion is achieved. Very low optical loss, less than 0.5 decibel per centimeter. Very high isolation, higher than 30 decibel. High Faraday rotation, larger than 260 degree per centimeter. And wide operation range for the optical isolator.